In this video, we're going to continue with chapter 3, hydrostatic forces on submerged plane. So you have looked at a horizontal plane and vertical plane in the previous videos. Yeah. So just to recap, this is for the vertical plane, and if you are confident with this, you can proceed with this video. Otherwise, I advise you to go to the previous video and also go through the solved examples. The solved examples are not in video format, they are in PowerPoint format. You can find them in week 3 folder. So those examples will really help you understand the vertical plane examples. Okay, but if you're confident, you can proceed with this video. So in this video, we're going to talk about the hydrostatic force on submerged inclined plane. So inclined meaning that the plane is not horizontal, it's not vertical, but it is inclined at a certain angle. Here the angle is given as beta. Okay, we still have the same equation, Fr equals to PCA. So let's see what we have based on this diagram. So A is the area of the plane surface. Of course, this is the side view of the plane. Yeah, so the plane surface will be viewed from this angle. Okay, and the plane surface from here, you can't tell what shape it is. It could be a rectangle, it could be a circle, it could even be a triangle. Okay, so we need to know the shape of this plane. And then we have point O, which is the intersection between plane and the free surface. So just like before, this indicates that this is a free surface. So if the plane is fully submerged like this, you can just extend the line of the plane, and where it crosses the surface is point O. And then we also have centroid, which is the center of the area. So this depends on the shape of the plane. So assuming this is a, let's say, a rectangle. So obviously the center is at the center here, which will give you C at this point, right? And then we have center of pressure, just like in vertical plane, it's always lower than C. So let's mark it somewhere there. And then we have Fr as the magnitude of the resultant force, and this is always perpendicular to the plane. So Fr is resulting force coming from the pressure here. And notice that the pressure distribution is still uneven in the case of the inclined plane. So we have some pressure here, and then it keeps increasing because it is going lower underwater. So it's not increasing as much as in the vertical plane example, but it is still increasing because from this point to this point at the bottom here, the rho GH increases. Okay, so we still have this profile, and therefore Fr is acting not at the center but at CP. And then we have YC. So instead of HC, we have YC, which is the inclined distance from O to C. So that should be here. Okay, O to C. And we have YP, which is inclined distance from O to CP. So quite clear here. And YP can be calculated the same way we calculated HP in the vertical plane case. Alright, so the difference here is that we are using YC and YP instead of HP and HC, because it's easier that way, because we can work on the plane orientation. We don't have to convert everything to the vertical, right? But if ever you need to, the relationship between H and C can be seen here in this triangle. So let's say this is YC. Yeah, you have your YC here, and you have an angle here. So I'm going to put the angle here. You can easily find the vertical height. Okay, the equivalent height of this point C here using this relation. Alright, so here you have the same moment of inertia information which you can refer to. Okay, so let's go to one example. So here we have a water. that is 25 meters deep in a reservoir. It's kept inside by a 150 meters wide wall whose cross section is an equilateral triangle. PATM is 100. Okay, pause. Right? We have water and it is being kept here in this reservoir by a wall, and the height of the water is 25 meters, and it says that the cross section of the wall is an equilateral triangle. So what you're viewing here is not where the pressure is acting. Obviously the pressure is acting only at this side, right? So the wall is still a regular wall. So viewing it from this angle, it is a rectangular wall. But from the side, if you cut it across, you get that the cross-section area of the wall is a triangle. Now this can be easily explained by having the need of a thicker wall at the bottom, because higher pressure at the bottom, so you don't want the wall to collapse at the base. So if you recall from the very first picture of this chapter, there was a picture of a dam, and the dam has a thicker wall at the bottom. So this is the case. Yeah, but of course the wall, in order for it to be effective, it still has to be a full rectangular wall, right? Okay, so we have to determine the total force acting on the inner surface of the wall and its line of action. Okay, so before this, we have conveniently ignored the atmospheric pressure because it acts on both sides. Now here, the question wants you to include the atmospheric pressure when calculating the total resultant force. Okay, and the line of action means YP. Right, next you have to find the magnitude of the horizontal component. Okay, this should be easy. So we solve for A first, yeah? To solve this, we start with this equation, Fr equals to P times A. Now here, the P is not written as rho GHC because you need to add PATM to the rho GHC term. Because before this, we've been ignoring the atmospheric pressure. Now you have to include PATM plus the rho GHC. Okay, and PATM value is given here. So this is total pressure times the area. The area here is the area of the wall that is in contact with the water. So obviously it is not this triangle, right? It is the other side that you don't see. It's a view from here. Okay, it is a view from this plane. All right. Now let's see the values. Okay, C is the centroid of the wall, because assuming the wall is a rectangular wall, which normally a wall typically is, so the center of the area will be at the center of this, yeah, of the side here. So this should be your position for centroid. So putting in the values, we have PATM as 100,000 Pascal or newtons per meter squared, and then rho is 1000. This is gravity. HC, so as I said, the centroid is here, therefore you can just divide 25 divided by 2 will be 12.5. So why are we not taking the YC here? The reason is this 12.5 is referring to the pressure, hydrostatic pressure. So you can't take the YC because we know that the pressure is measured vertically. Remember, in all the manometer examples that you've done, pressure is measured vertically. So it has to be H. Okay, so this is area of the wall that is in contact with the water. So the width of the wall is 150 meters. We don't see the width in this diagram. The width is going into the screen. Okay, and the other edge, which is the height, will be 28.87. Where this is coming from is here. Okay, and we don't take it until the top, but only until where the water surface is. So from here to here. And to calculate that is using 25 divided by sine 60. I think you can work that out. Okay, and you get the resultant force. So next is what is the line of action? That means where is this resultant force acting on? We know roughly that it should be somewhere lower than C, but where exactly? Okay, so I'm going to label CP as somewhere lower than C. This is your value for C, YC. Okay, and to get the number, you can work it out using the angle. And this is what we want to find, YP. What is the distance from the surface to CP? So I naught is from this equation because it's a rectangular plane. We use this for moment of inertia. And the area of the plane, the YC, if you calculate, you should get 14.44. So you can pause this video and draw the triangle. Okay, so area is the same area as here. So you can just take this number. So solving, okay, and the final answer should be YP equals to 19.35 meters. So again, YP is from the surface to this point. You can, of course, find the HP equivalent for this, but it's not necessary. Okay, now for part B, what is the magnitude of the horizontal component of this force? So FR is here. Okay, this is the resultant force. So what is the magnitude of the horizontal component of this force? So that should be very simple. You know that the force can be broken down into Fx and Fy. So horizontal component means you find the Fx component. So here you can work out the angle, and this angle here should be 30 degrees. So the Fx component of the resultant force should be Fr cos 30. Alright, so this is the end of the video. I'll see you in the next one.